Hello, I'm David. This is a revision seminar for Multivariable and Complex Calculus at the University of Adelaide and Semester 1, 2025. I've said this in several of the seminars. This is the last version of this course. Hopefully we'll get a new version in the new university that be combined with whatever UniSA's version of this is. So fun times. Whole new, get to learn all the content again. Sure, hopefully it's not too different. All right, well, after that little thought, we're going to get started. And I've had some requests. And as much as you said, if there's time, can we talk about Laurent expansion? I want to do that first. Because integration is my favorite bit, and I want to leave that to last. So, yeah. All right. Well, Laurent expansion is for usually used for the purposes of doing integrals in complex numbers. We'll have to get some people to check up on the details, but I'm going to try my best to remember it because it's good to do that, to try to remember things, and you should do it too when you do things. I do have a question. Do you get to take your own notes? No? Big no? Okay. Is there a page of formulas and things that they give you? Have they given you that page already in advance? Okay, good. That's the next best thing. Okay, excellent. I'd love to see it. That'd be lovely. Oh, look at that. For the purpose of copyright, I didn't write this. This is written by the current lecturers of this course. And it looks like all other maths does when it's written in LaTeX. So there you go. All right. Please ask for it back. Okay. I just need to put the mic on because even though it will be quite loud, it will save my voice a little bit. And it'll make it easier for the mic on my computer to pick it up. Okay. Why is it the moment you put the mic on is when you need to cough? Okay. So they're usually used for the purposes of doing integrals in the complex numbers. And yeah, that's pretty much the deal. And so we're going to have to talk about those integrals along the way in order to do it. So just a second. Let me be. I'm just organizing my thoughts. Okay. And the kinds of integrals that we're going to try and do using Laurent's expansions is of the flavor of this. Something like that, where, oh crap, I've used C for both of them. I'll call this one gamma, where gamma is a path around the point C, something like that. It's designed for use in this sort of situation, and where this is an analytic function here, and this is that. That's what it's designed for, and it turns out that the one of the coefficients in the Laurent series is the one you want. Yeah, so that's the idea. So the reason I wrote that is just for my own purposes to get to the point where I wanted to, which is that this thing here is what the Laurent series is all about. So the idea is that if you have a function that is analytic at a particular point, so if f of z at z equals a particular center, I'm calling it C, your lecturer probably calls it Z0. Is that right? Yeah. Sure. I like to call it C for center, but that's just, yeah. If f of z is analytic at that point, then it'll have a Taylor series. Which will go something like, you know, A0 plus A1z minus C plus A2z. Damn it, I did it again. Z minus Z0 squared plus, and so on forever. And it may be that it's a polynomial already, in which case there'll come a point where the coefficients are 0, because it's like, you know, it's a degree 7 polynomial, you won't be able to go past the 7th degree. And it may be that it's not a polynomial already, and it's something like e to the z, in which case you'll be able to, it'll go forever. And then the correct answer for what goes in this spot is the nth derivative at z0 of your function divided by n factorial. That's the correct thing to go in that spot. That's Taylor series. Cool. And the most famous Taylor series are the ones where Z0 is in fact 0, and it's just a Maclaurin, and it's called a Maclaurin series then because everyone thinks that Maclaurin deserves some glory for inventing this idea, even though Taylor made it more general and wrote the theorem. So, yeah. So, okay, so that's Taylor series. Right. So the thing is that if you then divide f of z by z minus z0, I'm just going to put a k there instead of an n, because the n I've already used here. Then it will in fact begin with a0 z minus z0 to the minus k, and a1 z minus z0 to the minus k plus 1, and so on. And then at some point, you'll get to the bit that would have had z to the minus z0 to the power of k, and you're going to divide it by z0 minus z0 to the power of k, and so you just get a plain number, and then you get a k plus 1, z minus z0, and it'll keep going from there. So what you end up with is a series that looks like a Taylor series, but it begins in the negative powers. This here is a Laurent series. Yeah. Now, traditionally, knowing that you're going to get something with a negative power, we actually usually call this a negative k and a negative k plus 1 and so on. So I've borrowed the coefficients from the original f, but normally you'd actually write it as like this. You'd normally go, if you had, you know, a random function g of z, then you'd normally say like g of z is a negative k z minus z0 to the power of negative k plus a negative k plus 1 z minus z0 to the minus k plus 1 and so on forever, like that. You'd normally label them by the power or the exponent there, rather than labeling the first one a0. But that's the deal. There's no particular reason you have to call them by any particular name, but that's the tradition. So if your function is not horrifying at the point z0, it will have a proper Laurent expansion that does start at a particular negative k and go up from there. But some functions are horrifying and they don't have Laurent's expansions. Like it has to be particularly bad, like because this function already doesn't have a Taylor series at this point because it has negative powers here. And so it's already pretty bad, but it was really bad if it doesn't even have a Laurent series. So yeah, and I imagine it would be really difficult to create a function that did that. So yeah. Stopping at this moment to see if anyone wants to say anything. Yep. Oh, good. So you're understanding why the residue becomes the coefficient of a to the power of a negative 1. Yes, I was going to talk about that, so thanks for reminding me. Okay, so that's the Laurent series. And just as an example, you can find them from Taylor series. That's usually the easiest way. But you can also find them from derivatives as well because of the Taylor series. I'm pretty sure. This is where I may have to have a quick squeeze at the notes. Yeah, but I do know that as an example, if you had like something like that, e to the z over z minus I, that would have a Laurent series with center I. It'd have an ordinary Taylor series with center 0, an ordinary Taylor series with center anything other than I, but it'll have a Laurent series for center I. So we'll have a Taylor series center 0 or 1 or 1 plus I or any other number, and it will have a Laurent series with center I. And that Laurent series will have z minus I to the negative 1 at the beginning. And the reason I know that is because this is analytic. And so e to the z is e to the z minus I plus I, which is e to the I, e to the z minus I. Don't like e to the I, but there you go. I guess that'll be cos of 1 plus I sine of 1. And so, and this, I know because of how the Taylor series for e to the x works, this will be 1 plus z minus I plus a half of z minus I squared plus 6 of z minus I cubed plus blah, blah, blah. And it'll be 1 on n factorial z minus I to the n. And so therefore e to the z on z minus I will be e to the I 1 on z minus I plus 1 plus a half of z minus I plus a 6 of z minus I squared plus and so on. That's the Laurent series. Yay! That's it. And so what we have is the coefficient, for example, of z minus I to the minus 1 is e to the power of I. Yeah, that's all. I mean, we could have done it with an actual infinite sum at that point, and that would have been fine as well. So I guess I could have done this if I wanted, or either the y times z minus I is e to the I sum of n equals 0 to infinity z minus I to the n over n factorial. And therefore, that e to the z over z minus I z minus I to the n minus 1 over n factorial. And so if I really wanted to start at minus 1, which I know it does. So when I put n equals 0, the first one's -1. And so if I really wanted it to start at minus 1, I could subtract 1 from all of these and add 1 to all of these. And now that looks like a proper Laurent series because the n is the power of the actual, including the negative power. And so I could say, oh, what is the coefficient of z minus 1 to the 5? It would be 6e to the I on 6 factorial. Cool. I don't know if that's important, but this is an alternative way of doing it. You can write it with the dots or you can write it with a sum. Are you feeling okay? Yep. Oh, sorry, that's an I. Sorry. Thank you. Just forgot to put my dots on. So what I've done, so it should be an I. Sorry about that. Just wasn't paying attention. It's tradition for Laurent series to actually write the n to be the actual exponent that's actually there. And so I want this to just say n. So I add 1 to both of these and subtract 1 from all of these, and that produces this index shifting like you do in differential equations.
Hey, but how do we go from z minus 1 to we found z minus 1, n minus 1? Like the line before is identical to the other.
I divided by z minus I.
Oh,
Thank you for being more precise about what the question was. Yeah, so with this one, the reason it went down by 1 is because I divided by z minus I. Yep. And so it made all the powers go down by 1. Yay. And most of them, it's so a tradition to just use the Taylor series you already know. Though you can do it from derivatives because you know that this is how I always get it wrong, and I'd have to look it up. There is a way of getting it from the derivatives. I know that if you've got the numerator and you do its Taylor series, then I know what the coefficient for that is. And so you could therefore know that the coefficient of z minus z naught to the m in f of z over z minus z naught to the n to the k is, damn it, don't know how to do that. So does that have a formula for this in your notes? But I can do it because I need to find the correct coefficient of this. So it'll be f, the correct derivative with z naught subbed in, divided by the thing factorial. Yep. That's what it will be, because it will be the correct coefficient of that. And I know that it will be m plus k, won't it? Because I know that all the powers in this are k lower than they were before. And so to figure out where the coefficient came from, it came from the power that was k higher. Yeah, that's that. That's what it is. So if I wanted the coefficient of z minus z naught to the power of -1, then I would need to go to the k minus 1 coefficient of the numerator. Because when I divide by z minus z naught to the k, I'll be left with a -1 power. So just to be absolutely certain, f of z will be whatever it is. I will use it as a b so that we can, no, it's fine. a m plus k z minus z naught to the m plus k. And then when I do this, z minus z naught to the k, I'll get a m plus k z minus z naught to the m, like that. And so this coefficient from the original Taylor series becomes the coefficient of the power that I want. Yeah. But importantly, the really important one is z minus z naught to the power of -1, which is the coefficient of that, which is z minus z naught to the k, which is f of k minus 1. The k minus 1th derivative is that one. Rubbing n equals k minus n minus 1 into the thing above. That's a really important one. And the reason it's really important is what you asked earlier, and so we'll do that. Yeah. Okay. Yeah.
Identifying the coefficient, the line for substitute n for f of z over z minus z over k. Can you also use, I think in the notes they just use summation, and then they say, because we write the Taylor series in a summation format like we had before, can you just use it by changing the variable? Like if
Yeah.
aj, you have to find aj in terms of k, and then you just have that and the corresponding.
Yes, you can change the variables.
The same as that, right?
It's exactly the same as that. But this was me trying to figure out how to do that without actually writing it down. So just figure out how they line up to each other. Yeah. Cool. Okay. So yeah, most people just use the Taylor series as the series that they know to figure this out. And there are four classic Taylor series that most lecturers expect you to know, which are e to the z, which is that, and cos of z, which is the even ones for this. And they alternate between plus and minus. And sine of z, which is the odd ones of e to the z. And they also alternate between plus and minus. With the first one being positive. Just so you know, cosh is the same as cos, but without the -1 to the end. And shine is the same as sine, but without the -1 to the end. So that is not a z, that is a 2. Yeah. And there's one more, which is famous, which is this. 1 over 1 minus z. Which is just z to the n. Geometric series. Yes. Yep. MCC lecturers traditionally expect you to know these. It's one of those things. Yeah. Which is interesting because you didn't live in a land where you had to remember them in the past. Yeah. So, but they are ones I've shown you. I mean, I can just remember this one. And this is a geometric series. And this one I showed you how I remember it, which is as well as the even ones for cos and the odd ones for sine. Yeah. It has to be a 2n plus 1 so that when you sub in 0, it comes out to 1. Yeah. Yeah. That's why cos is an even function, or vice versa, because cos is an even function, it only has even powers in its Taylor series. That's why functions that are even are called even, is because they behave the way that even powered polynomials work. Okay. They certainly don't behave like even numbers. I'm just going to make sure I don't lose the order of my pages. So it turns out that Laurent series are kind of related to things. So it turns out that the z minus z naught to the power of -1 coefficient is the residue of the function at z naught. So that's not the definition, but it turns out that the coefficient of z minus z naught to the -1 in the Laurent series for g of z is the residue. Is that got a small r? Yes, it does. Is the residue of g at z naught. Is that right? Cool. That's how it turns out. And it's amazing that this is true, but it's not that amazing. And the reason it's not that amazing is this. And thank you to the student I was with in the Maths Learning Centre the other day where we looked this up. Was that you? You? I can't remember. Anyway, I was with someone in the Maths Learning the other day and we looked this up and I feel so much better about it. So hopefully I can pass that on to you. The definition of what the residue is isn't this. The residue is defined to be the residue of g of z naught is defined to be the integral of around c of g of z dz for a curve c containing z naught as the only singular point. Divided by 2 pi I. Right. Yay. Okay. That's what it is. That's what the residue is defined to be. So you define the residue as the thing you have to multiply 2 pi I by to get this answer. So theoretically, if you wanted to find the residue of a function, you could totally parameterize a curve around z0 in such a way that the curve didn't contain any other singular points, and do the integral with the parameterization. You'll get an answer, and you divide it by 2 pi I, and that's what the residue will be. But it happens to be that the residue is also the z minus z naught to the power of -1 coefficient in the Laurent series. Which is just fabulous. And the reason why it is this. Are you ready? It's very cool. It requires a lemma. And the lemma is this lemma. The lemma is that this integral for c containing 0. I mean, it's an anti-clockwise curve containing 0. So we're imagining here's 0 and C is like that. Always comes out to 0 unless z equals m equals -1. So that integral equals 0 for m not equal to -1. That is it's not called a lemma in your notes, but it is definitely, I think, cool and important enough to be given a proper name. I mean, maybe not important enough to be a theorem in its own right, but it may be a lemma. And you can do this by straight up parameterizing it. Straight up parameterizing z, and just use the circle around, use e to the I theta. And so this can be proved by doing z equals e to the I theta by doing that substitution for the curve. And if m is -1, this is just 2 pi I. Which is a person's theorem, or possibly like Cauchy's theorem. No, Cauchy's theorem is that for an analytic function, the integral around a curve is 0, right? Is that Cauchy's theorem? And Cauchy's formula is that if the numerator is analytic, if you divide it by z minus something, then the integral is 2 pi I times the function value of the top. Yeah? Yep, this is the most special case of that. Because the analytic function is 1. And it is always 1, no matter what you sub into it. So this will be like times 1. The residue is very similar to this. But the residue is designed for things that aren't just 1 over z, but also 1 over z squared and 1 over whatever, and for some other function divided by z squared. That's the issue. So, yeah, they're very, very similar. So, blah, 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 blah. This is 0 if that power exponent is not -1. And this will work perfectly well if we change the center. I'm just putting in a different spot. It'll work the same. And so this works even if it's z minus z naught to the m. So it also, we can just adjust this to say the integral around c of z minus z naught to the m dz is 0 if m is not -1, but the integral of z minus z naught to the -1 dz is 2 pi I. Okay. And using this, if it does have a Laurent series, so if g of z is like a minus k z minus z naught to the minus k plus 1 plus a minus 1 z minus z naught minus 1 plus a naught plus a1 z minus z naught plus blah, 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 blah. When you do this integral, and this contains z naught, then this integral will be 0 because the lemma says so. And so will all of these, those will all be 0, and all of these will be 0, and you'll end up with just this integral here, which is a minus 1 times 2 pi I. So you will end up with 0 plus 0 plus the integral plus 0 plus 0, blah, 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 which is a minus 1 times the integral z minus z naught to the minus 1 dz, which is a minus 1 times 2 phi I. Magic. It's the cutest and stupidest thing, right? But, you know, stupid in the sense of we've set up all of this really, really clever stuff to make it seem stupid. So, yeah, there you go. And that is why it is the way it is. And since it is the A-1 term in the Laurent series, that must mean that you get it by differentiating your function 1 less than k times and subbing in the center. And so if you have a function that is, so if you have, so if g of z is f of z divided by z minus z naught to the k, and this one's analytic, then the residue of g at z naught is going to be the k minus 1th derivative of f with z naught subbed in. Yep. Divided by k minus 1 factorial, because that's how you get a Taylor series. And on this thing here, if you look very closely, they've put f in the spot where I put g. And when you multiply it by z minus z naught to the k, you just get the numerator. So this is saying that if you differentiate the numerator, k minus 1 times, divide by k minus 1 factorial, and then sub in z equals z naught, then that's what that means. They have put a limit there because I'm sure they're just covering all their bases, because technically it doesn't have to actually exist at that point. It just has to have a limit, but whatevs. In almost all of in every one of the example questions that any student has ever showed me, you don't have to actually do a limit. You just sub it in. Yeah. Isn't that fun? So there's these 3 things now that we've said the definition is based on the integral around the problem point. The singularity, is that what they call them? No? Pole? That's another word, isn't it? Around the problem point. And then it turns out that if you do Laurent series, that integral is the same as just this thing times 2 pi r. So, yeah. There you go. Yeah.
What?
I don't know. Residue just means thing left over after you do something. So it could mean literally it's the piece left over after you do all these integrals and there's only one left. That may be why it's called that. And so that means it's kind of circular reasoning, no pun intended, but it's circular reasoning in the sense that they've maybe named it after the thing from the Laurent series, even though it wasn't defined that way. I don't know. I could be wrong. I haven't looked up the history. But that makes sense to me as a word. It's the residue is the leftover bit. You know, the dregs left at the bottom after you've drunk the coffee. That's the residue. So yeah, maybe that's why it feels like it's left over. So it seems to me when I think about this whole residue theorem and Laurent expansion and stuff, that this lemma that I mentioned with this here, these facts, they're important things to remember, I think. Yeah. So for the positive m's, this is Cauchy's theorem, right? Because an analytic function that integrals 0. But for the negative m's, like -2 downwards, it still comes out to 0 anyway, which is amazing, really. And it's mainly because you get exponents. You can actually integrate z to the -2. You can't integrate z to -1 without using ln, and that's what causes the issues. So, there you go. Feeling all right? Okay, so bear with me. I'm just going to number my pages and then answer that question. Okay, so you said, I'm just going to repeat that question. When you're doing an integral and there's singularities inside the curve, you've got to worry about the residues. And when there's singularities outside the curve, nobody cares. What happens if the singularity is on the curve? So I'm just going to draw all three of those situations. Singularities inside, you'll have like 2 pi I times the sum of the residues. Something like that. And then singularities outside, who cares? It's fine. Everything will be okay. If the singularity is on the curve, that means the integral doesn't exist. It may technically be possible to do an improper integral and still get an answer if it approaches infinity in just the right way. But the singularity is usually a place where you're attempting to divide by 0, which causes the answer to be plus or minus infinity, or in the complex case, one of the infinities in one of the different directions around the circle, because for the real line, there's only 2 infinities, but for the complex plane, there's infinities in every direction. So that'll cause your answer to be infinite, and so the integral doesn't exist. Yep. What if the curve is what? If the curve is clockwise, it'll be okay. It'll just be minus what it was before. But yes, you're saying if it's clockwise, doesn't that mean the ones on the outside are actually on the inside? No, it doesn't. It just means that if it was this way, that would be minus 2 pi I times the sum of the residues. Yeah. Probably Zi, I guess. Yeah, so it doesn't mean that the ones on the inside are now on the outside. It just means that it's minus what it was before, because it's traced in the opposite direction. But that was true. Tracing a path backwards back in the real numbers produced minus the original answer. Like if you do the integral from 1 to 3, you'll get an answer. And if you do the integral from 3 to 1, you'll get minus what it was before. Still true in the complex numbers. So nice. We don't have to, but that makes sense. It makes sense that maybe going the opposite way, the ones on the outside are actually on the inside, but no, that's not how it works. Convenient. That's much better. Yeah. Cool. So ultimately, you're supposed to imagine like retracing your curve so it goes around each little bit as little duvas like this with this homotopy thing. But in the end, it doesn't really matter. Like, you know that that's happening, but you don't have to actually draw that. You can just add up all of the residues and multiply by 2 pi I, and that should do it. You just have to, I will say, you must draw the picture, though, to know which ones are inside the curve and which ones aren't. Because there was an assignment question this year where there were 4 singularities, but only 2 of them were actually inside the curve. Yeah. And in the part B, none of them were inside. Like, yeah, you can move the curve and you'll get different answers. Yeah. Cool. So with an analytic function, it doesn't matter what path you go from one place to another, you'll always get the same answer. But with a function with singularities, it will depend on which side you go around the singularity as to what the answer will be. Yeah. So I will say that if I did the integral has z equals z naught, and there's z naught. If I did this path, I would get a different answer than if I did that path. Those two paths will give different answers. The integral from C1 of f of z dz will not be the same as the integral C2 of f of z dz in general. But if I did these ones, they'll all be the same. And these ones will all be the same. But if the path has to go, if it goes around the, and this one would all be the same. But if it goes around the opposite side, it will get a bit different answer. Yeah. So if you have to move this curve through that point to get from one to the other, they won't be the same answer generally. Yep. And in fact, I know for sure that the integral C1 f of z dz plus the integral of, oh, that's C2, sorry, minus C2 going in the opposite direction, f of z dz will be 2 pi I times the residue, will be 2 pi I times the residue of f at z naught. Yeah. So it could come here, go around, come round there and do that. Yeah, so the two of them together, one of them one way and the other one backwards, together are a curve that do go around z naught, and so they will together be 2 pi I times the residue. Yeah. Yeah.
Just for
Correct. So for, I'm going to say that so that it appears on the video. If you have from A to B of f of z dz, something like that, you can only write this if f is analytic. So so this is equal to technically a curve dz where C starts at A and ends at B, right? And this will only be independent of the curve if f is analytic. So it's only of par when f is analytic. Yeah. Analytic everywhere. Because if f is not analytic at one spot, then there will be at least two different answers. In fact, if f is analytic at one spot, there will be, well, it depends, because if you loop around that point multiple times, then you'll get different answers again. So, yeah, so that happens as well. So if I had gone round, if I had had a curve that looped around that, that would have gotten a different answer again. Probably the same as C2, but if I went round twice, it would have another answer again. So you need to be careful of your curve looping around itself. But for an analytic function, it doesn't matter. It can loop around itself as many times as you want, and we'll just give the same answer. Yeah. Puzzling things, the complex numbers. We had to do a lot of work to define what integration even meant over the complex numbers. Yeah. Feeling okay to move on from this? So when I put this in the video, I will title it Laurent expansions, but it's actually Laurent expansions and integrals. Okay, cool. Wow. Okay. Yeah. So that's why it's totally okay to do this when you've got e to the z here, because that's a perfectly good analytic function. And if you've got a path that goes from, say, 1 to I, then you can just do the antiderivative and sub in I and sub in 1 and subtract. Yeah, but you know that it'll always produce the same answer, so it doesn't matter how you do it. I even think of that question. I just had a thought before I finish that off of it's not going to be a proper finished example, but I just had a thought that what if you had something like that's the one that I have here, right? And I've got C, and C is the line from bear with me, 0 to 1, right? No, not from, wait. Not the line from 0 to 1. Doesn't matter. This is going to be C2. Just going to draw a picture of it so I can describe it. C2 is as pictured. Like that. That's C2. And this is C1. I could imagine, I'm not sure that a friendly lecturer would do an exam question like this, but I can imagine an assignment question that would be to not give you this one and to just say, find this integral. And then you could find this one using parameterization, and then use the fact that together they are 2 pi I times the 2 pi I times the residue to figure out what the other one had to be to complete the circle. So that would be my nasty question just to myself. So I could do so C1 is like just T for T between 0 and 1. It's a perfectly good parameterization of that. Z equals T. Yep. And so dz would just be dt. That's fine. And I'd have the integral from t equals 0 to 1. Integral c1 of e to the z over z minus I dz would be the integral t equals 0 to 1 of e to the t over t minus I dt. Oh, crap. I don't know how to integrate that. Okay, that's okay. It was worth a try. I'd have to use integration by parts. It would turn to crap, wouldn't it? No, it's worth it. No, bad. Sorry. Bad. Oh, dear. No, ignore this. Sounded like a good idea. But they could totally just tell me what this answer is and then ask me what this answer is, for example. That would totally be a thing. Yeah, they could do that. Yeah, they could say this answer is like 2 pi or something like that. And then say, what's this answer? Ah, well, overall, the answer is blah, blah, blah. Ah, yeah, let's do this. This answer is like R. And then find this. Yes, that's the question. That's the exam question. I love it. They tell you that this integral is R, which is a complex number, and they ask you what this integral is. Yep. And I say, I'm just going to cross that out. And what I say is, well, I know that the integral C2 e to the z over z minus I dz plus the integral of minus C1 e to the z minus I dz, because that's the opposite direction, because we go around. Oh, crap. No, we want to go anti-clockwise, don't we? Sorry about that. So C1 and then anti-clockwise round there. That'll be 2 pi I times the residue of e to the z on z minus I at I, like that, because that's what the curve is. It goes around that point. And we figured out that residue earlier. It was 1 times 2 pi I, right? That's what the residue, no, it's just 1. It's the coefficient of z to the minus I to the negative 1. So we figured that out earlier. 1. The page 2. See page 2. And so therefore, integral C1 e to the z. Wait. So this integral is going the wrong direction, so it'll be minus the integral that they've asked me for. And this they called R, like that. And so therefore the integral I want pop that over there, is R minus 2 pi I. Yay! Yep, I like it. That'd be a cool exam question, because you don't actually have to do any parameterization or whatever. You just have to find a way to write it down. And it'd probably be a part A where it says find the Laurent series of this. Yeah, A is find the Laurent series of e to the z over z minus I, and then it says this. Yeah, how are they related? So yes, because the minus 1 coefficient is the residue, and I can use the residue to find the integral. It's so good. Wish I was the lecturer now. No, because I don't really want to mark the exam. One of the best things about not being an ordinary everyday lecturer is that I don't have to mark the exam. Oh no, it's e to the I. Oh crap, you're right. Yep, it's not 1. E to the I. Yep. That's what it is. Good move. I didn't see, that's why I need a mistake theory. Because I forgot to expand this out to get the individual coefficients, because there's a number there. Yep, gotcha. Thank you. This is the sort of thing where I would go, if I'm in an exam, I just really need to make sure I don't forget to expand out numbers that are sitting on the outside. That's something a trap to keep an eye out for. Page 8. Okay. Yeah, it'd be a great exam question. I will laugh so hard if one of you comes back and says, oh, David, they told us to find the Laurent series, and then they asked us to find an integral. They told us one integral and asked us to find the other half of the curve. That would be the funniest thing ever. And great for all of you who are at this seminar. Okay, we shall talk about parameterization, because that was the first thing that was asked. Okay. Now, other things on this list were change of variables for integration and the theorems of integrals, Green's and Stokes and divergence. The thing is that in situations where you have to show that you understand those things, you are going to have parameterizations. You're going to have to do them. You're going to have parameterizations, or you can't do change of variables, or you can't do a raw path or surface or volume integral. So that's why it's such an important thing to people to ask me, and I'm very happy that you did. So, and I've talked about this in multiple different years, and so please feel free to go and watch the other ones if you still don't have a thought on it. But also know that if you come and talk to me in person, I may give you a whole different version of it if this one isn't working for you. So, yes. The thing I hold on to with parameterization and all parameterizations is that they are a description of what every point on the object is. And when I say object, I mean that it could be a line, it could be a curve, it could be an area, it could be a surface, it could be a volume, whatever. You have to describe every point individually. So in that sense, it's like giving coordinates to every point. And actually, that's what it is. It's a way to describe the coordinates of every point on the object. That's what a parameterization is for, and that is the information I hold on to. So when someone gives me a parameterization, it tells me what every point on the object is. And I look at it and I think to myself, okay, so where are those points? And if someone asks me to, or I'm required to, because of the system, to make a parameterization, I need to describe every point on the object one at a time. Like they all have to be described once. I'm not allowed to do any of them twice. That's the idea. And there are two parameterizations that you have seen in your life that you didn't know were parameterizations at the time. In fact, there are three that you have seen in your life that you didn't know parameterizations at the time, and they are these. All parameterizations that you already knew but possibly didn't think you knew already. And so we have one of them is a straight line from one point to another. And I know that with vectors, I can locate every point on here, between here and here, by figuring out what the journey between these is. Which is b minus a. And then going a fraction of that vector. So if t is 0, then I get 135 and I'm here at the beginning. If t is a half, I'm exactly halfway. If t is 3/4, I'm 3/4 of the way. If t is 0.9, I'm 90% of the way. And if t is 1, then I get this point. And so this is the journey from A to B. And that is a parameterization of a line from one place to another. And if you really, really want to, you can do this. If you really want. And that is a perfectly good parameterization of a straight line. That is exactly how you parameterize straight lines everywhere, including in the complex numbers. So if you want a straight line in the complex numbers, just going to be really, really there's A, this is B. That's going to be minus 1, 2 plus 3i. This is going to be 4. And so the journey from A to B is 4 minus the end minus beginning. That's the journey, which is 6 minus 3i. And each point, the points are minus 2 plus 3i plus t lots of 6 minus 3i. So perfectly good parameterization of the points from here to here. Yay. That's it. That is your first and most important parameterization, is a straight line. Your second parameterization that you know is a circle. Cos theta sine theta. So theta between 0 and 2 pi. Or from minus pi to pi, whatever, depends where you want to start and finish. But this one, in fact, starts here and finishes there. Great. So circles are so important because if you have an object in 3D space, a lot of them have circles on them, and you can build them out of stacked up circles. And this is the one that has radius 1. But if you have a circle of radius like r, that will be r cos theta, r sine theta. Yep. Doing okay? Do you wonder anything? No one cares, but yeah, traditionally you don't have to, you are supposed to only count every point once. Yeah. For the purposes of doing integrals, that single point at the end doesn't make a difference, but it does make a difference if you're just literally parameterizing. If you look very closely at your course notes, your lecturer is not going to be too fussy about that, and sometimes they'll have an or equal to, and sometimes they won't, and you'll just have to be okay with it. Yeah, so they are circles. And I will say if the center of your circle is in a different spot, then that circle there, for example, which has radius 2. You ready? This is the fun bit, right? So you see this point here, it's that point plus a piece of the circle. So this will be 2, 3 plus 2 cos theta, 2 sine theta. Pretty cool. You just shift the entire circle over, like you can think about it, this is the points on the circle, and then you add 2, 3, and the whole circle shifts over to 2, 3. And so you end up with 2 plus 2 cos theta, 3 plus 2 sine theta. I don't know if they do that sort of thing to you and put it in a different center, but there it is. That's that. Okay, so they are the two most classic parameterizations, but I do have one other parameterization to give you. This move, though, I will say, that move of saying, oh, the center's wrong, we'll just do the parameterization as if it was 0 and then just add that on. That'll always work for any parameterization at all. Yeah, just want to point that out. So,
In way you're saying you have a paragraph that is caused by the word parameter.
yep,
That's good.
that's the move. Make your circle and then shift it over. This, at the moment, the way it's written, looks like you started at this point and then you made these journeys outwards to the rest of the circle. That's an easy way of thinking about it as well, but addition works either way. So I can make the circle point first and then add this to them, which shifts them all over. Yeah, I did. I subtracted this point from both of them, and that made it from 0 to this. And then I did t to that, and then I added the original one back on. That's what you mean? Yeah. It's very cool. I quite like that vectors work that way. That's one of the things about how vectors work. You know what? I've never thought of it that way before. Because I think of all vectors as journeys and points. But I like that. I like saying, well, let's shift it back to the origin and then put it back again. Fun. So there is one other parameterization that you are familiar with that you didn't realize you were familiar with, which is the graph of a function. Like that. And so this is, you know, if this was like -1 and this was 2, 5, then this would be the points x and f of x for x between 1 and 5. It's a perfectly good parameterization. Y is f of x, so I just sub that in for 1. You didn't realize it, but it was a parameterization all along. Yay. Works perfectly well if your function's the other way around and it's like, you know, f of y, y. That could work if you had the inverse version of your function. Yeah. Okay. And in fact, planes, you can do this even in 3D, right? You can have some sort of surface here that's above a circle or something, maybe above a rectangle. A really bad drawing. But you can actually have x and y and f of xy. That's a perfectly good parameterization of a surface, as long as you know what the function of the surface is. If your surface is already a function, then you can do it this way if you want.
Back blocks.
Mm-hmm.
We had just a square. And for the kind of motivation of that, I'm not too sure. I think they used straight lines to answer, but how do an example?
We'll see how I go, but I can parameterize a square. So I will say that any object that is made of multiple different pieces, you can parameterize each piece separately. So if we had that square from 0, 0 to 1, 0 to 1, 1 to 0, 1 to 0, 0. Like that. Each edge will have to be parameterized separately. And so I can call this like C1 and C2 and C3 and C4. And so C1 will be T of 1, 0, because I started at 0, 0 anyway. And I'll go some fraction of that journey for T between 0 and 1. And C2 will be, okay, so the journey is this minus this, which is 0, 1. So 1, 1 minus, so that's the end minus the beginning, which is 0, 1. And so this will be 1, 0 plus T lots of 0, 1. For T between. Nah, I mean, you will add the integrals at the end. If you do an integral around this curve, you'll do each integral separately and add them up, and that will be the integral of the total. But when you parameterize the whole, I'm imagining this, when you parameterize the whole thing, you just say each curve separately has its own parameterization. You don't have a total parameterization for the whole thing. Yep, wait. C3. So the journey is from 1, 1, the end is 0, 1, and the beginning is 1, 1, and so that is minus 1, 0. And so this will be 1, 1 plus T lots of minus 1, 0. And then C4, the end is 0, 0, and the beginning is 0, 1. And so that's 0, negative 1. And so I've got from 0, 1 plus T lots of 0, negative 1. So they're my 4 pieces. And if I did the integral, so just as an example, if I did the integral of bear with me, f of x, y, ds around the square, right, like that. Yep. Yeah, that's flux. Is it? No, flux in 2D isn't a thing.
But could you say like it's a surface?
Yes, you could do it as it's, yeah, oh, well, you could do the flux. Right, that's a whole other, yeah. Yes. I'm just not going to do the flux at the moment. Flux is a surface thing. And this, currently, that edge isn't a surface. So it is.
Because you know what I'm thinking about the assignment, the first question, you Gass's theorem to like simplify the problem. It was a cube.
Yes. Yeah.
And they said you could think about it as 6 squared.
Okay, yep, that's a different thing. And I'll come back to that. I think I misunderstood the question. But if I was going to do this, which is not a flux, it's just a path integral, then where f of x, y was, say, no, I'll do it that. This is the path integral of a scalar, which you can do if x plus y squared, for example, just making up something. Then this would be the integral C1 of f ds and integral C2 of f ds plus the integral C3 of f ds plus the integral C4 of f ds. And I have to do each of those integrals separately and add them up to get the total final integral around the edge of the square. And then, if I just did the first one, then I know that along this curve, the position that you're at, they call it R in this course, don't they? the position.
Yes.
So along C1, let me just do, I'll do a different one. I'm going to do C3, just because I'm not going to do all four of them. C3 is 1, 1 plus t minus 1, 0, which is 1 minus t1. And then ds would be dr on dt times dt. Which would be minus 1, 0 dt. So differentiate the two coordinates separately. Look, and that's this bit. It's the coefficient of t. Isn't that fun? And so therefore ds is the length of this which is just dt. Look at that. Isn't that great? It's nice. And so therefore, and f of xy is f of 1 minus t1, because that's what the xy coordinates are. And that is 1 minus t squared plus 1 squared. And so therefore what I've got, what's that? Plus y squared. Oh, yeah, so I've done x squared plus y squared. So just x plus y squared. Okay, cool. And so that is 2 minus t. And so the C3 becomes t going from 0 to 1. The f becomes 2 minus t. The ds becomes dt. And now I just do that integral, which is 2t minus a half of t squared from 0 to 1, which is 2 minus a half minus 0, which is 1.5. Yay. And I'll do that on all four sides and add them up, and that would be the total answer. Sorry? It's not a flux, because a flux is the... You can do fluxes in 2D. Like you can do the flux. Yeah, that would have been, if it had been a vector field and a dot ds, that would have been a 2D flux. So that's okay. But the question you had was a 3D cube, which had a face on each side, which is a whole square. And to do the flux there, you need to do the integral across the surface, which means you need a parameterization not of the edge, but of the face. Yes, I was getting there eventually. No, I'm okay with that. I'm maybe in a minute, but okay. So just let me stop for a second. I will get there. Have a plan. We can make lines, and we can make circles. And if you only wanted a quarter of the circle, you would go from 0 to pi on 2. And if you wanted this half, you'd go from 0 to pi. And so you get to decide which piece of the circle you're looking at. So I will just put that comment back here. Note that this, just that bit is, cos theta, sine theta, the theta between 0 and pi on 2, for example. Right. Okay. Right. So parameterization of planes requires you to describe every point on a plane. I'm not going to give you a general way of doing this at this time, but what I can show you is that if I had a cube, traditionally a cube was probably from -1 to 1 in all three directions. Is that what it was in the assignment? Or was it from 0 to 1?
No, in the points where like I 0, 0, 5, 0, like
Ah.
but that's okay. I just want to see how they would find the flux through.
Yep.
It doesn't really matter what the question is.
So if I had, yep, I feel like I want to come back to that. Just bear with me. Okay, so I will do one thing. If I connect a triangle like this, then there's a little triangle there, which is a plane. And parameterizing that is quite difficult. Just that triangle is quite difficult to parameterize. Squares are much easier. But I do know that I should only need 2 coordinates for that because it's a plane, like it's a surface. So if this was, say, 3 and 2 and 4, for example, on the axes, then I actually need a way of figuring out where all the points are. And this parameterization is difficult to describe, and usually you have to figure out, I know the x's can go from 0 to 3, but the y's will be different depending on what x is. And so you didn't call this parameterization back when you did integrals, but you can do a flux across this surface if you want to. And so you can describe every point on this surface by first picking so from above, I'll look at it from above first. Like that. And the plane comes all the way back here. So looking down this way, it looks like that. And so I need to choose, if I can find a formula for this graph, for z equals, then I can do my parameterization as x, y, and z. So I know that I can locate every point down here by picking an x and then picking a y based on that. So this line here passes through 3 and 4 on the x and y axes. And so I can write it as like y equals 4 minus 4/3 of x by using slope if I want. But I can also, and that's useful, right? I can go y equals 4 minus, because that's the y-intercept and that's the slope. For every 3 across, it goes 4 down. And so that means that I can choose my x's between 0 to 3, and then choose my y's from 0 to whatever x was. That's a thing I can do. And then once I've chosen my location for x and y, which is about here, then I have to go up to where z is. Right? So how do I figure that out is the question. And I will tell you. I don't know if the lecturer won't care. There is a different way of creating the equation of a line, which I love very much. It's called the intercept form of the equation of a line. And an alternative for it is x divided by 3 plus y divided by 4 equals 1. So you go the x divided by the x-intercept, y divided by the y-intercept equals 1. And that is the equation of a line that has x-intercept 3 and y-intercept 4. Isn't that cool? So that's the alternative version of that. For our plane, it would be x divided by 3 plus y divided by 4 plus z divided by 2 equals 1. That is the intercept form of the equation of a plane. And let's just check if it really passes through these 3 points. When the point is 3, 0, 0, I get 1. And when the point is 0, 4, 0, I get 0, 4, 0, 1. And when the point is 0, 0, 2, I get 1. So all 3 of these points satisfy this equation. It must be the equation of the plane. Isn't that cool? I love it so much. And so that means that z is in fact 1 minus x on 3 minus y on 4. And so that means that z is 2 minus 2x on 3 minus y on 2. And so the points on this thing, the x's can be chosen from 0 to 3. The y's are chosen from 0 to 4 minus x on 4/3 of x. And if I want to be actually on the plane, z is just equal to this. That is a perfectly good parameterization of this plane. If I wanted the space below the plane, then I would have gone from 0 to this, and that would have covered this entire line up here. So this is the plane itself. Yep. So they are perfectly good ways of locating every point on a plane or every point in the pyramid below a plane. I don't know if it'll turn up, but I like it. There is an alternative to this. It's a little harder, but you can make these vectors and say that all the points on the plane would be a combination of those two vectors. But it's hard to figure out exactly where that line is. But if you were making a parallelogram, that'd be great. So I'm just making up stuff. I don't know if you're supposed to remember it. If I had something like that, that looks awful. Too late now. If I had a parallelogram which passed through this point, that looks more like 3, 4, 1, and 2, 5, 3, something like that. Then I know that every point on this parallelogram is going to be some amount of this vector plus some amount of this vector. So I could actually say that everything is like S of 2, 5, 3 plus T of 3, 4, 1. For S and T being in 0, 1, if I wanted. Because I can just go halfway and then 3/4 of the way. And if it was a parallelogram, it would work. Yeah. Okay. Yeah, and that's because every point in this plane is a combination of the two vectors. Yeah. And that's from Maths 1A. And if I don't want to go further than this, then I don't want to go further than one of these. And so if I do it this way, this is very similar to the parameterization of a single line. Yes. And even better, you could think of it as first going some distance of this, and which is this bit, and then going some distance of the other vector, which is this bit. With the plus here. Yeah.
This gives uses for plus.
Yes, this gives every point individually on this plane. So this is T lots of 3, 4, 1, and this is S lots of 2, 5, 3 here. And we add them because when you add vectors, you put that parallelogram together.
That was my question.
Cool, awesome. I knew we'd get there. So they're all great things. I don't know which ones you have to remember and which ones you don't, except the circle. You definitely have to remember your circle. And then here's the thing. There are even more creative ways to deal with things when they're curved, but all of them are based on some sort of circle idea. I know I said I'd finish at 1:45, but the next one starts at 2. So I'll finish then. Everything else is based on circles. So if you wanted to parameterize if you wanted to parameterize, for example, surface S, x squared plus y squared equals 4. No, let's not use 4, let's use 9. And z between 2 and 5. That's a perfectly good description of a surface. So this here describes a surface because it's a single equation in x and or y and or z equals a number. So a single equation involving x and or y or z will always describe a surface of some sort. But this is the version of making a surface which is, well, this could have come out to lots of different numbers, and today it's come out to 9, and I'll color in all the points in space where it comes out to 9, and that will be my surface. So there's that version of making a surface, but a parameterization is the opposite, where I describe individually what every point is. And so I need to imagine what this looks like. So I know that from above, it looks like a circle of radius 3. So that's the other thing to know, that x squared plus y squared equals number is a circle. So we need to know what that is. And there's my circle. I'm going to have 3 cos theta, 3 sine theta in my x and y coordinates. But that circle is actually, doesn't tell me what z is, and so it can be at any height. And it's only from heights 2 to 5. Like that. And so I can say, whoa, that's just reminding me for the problem stats seminar. I can say that this would be 3 cos theta, 3 sine theta, but that's only the x and y coordinates. I'm just going to leave space here in that spot there. And actually the z coordinate, it can be whatever you want. And so it's just z. And so I have that the theta goes from 0 to 2 pi, and the z goes from 2 to 5. And that is my parameterization. I can have any z coordinate I want. It's great. It's grand. But it was based on making the circle. What about this one? It's I've made one small change. Instead of it being equal to 9, it's equal to z. That's got a different radius for different z's. So it's still a circle. So from above, still a circle, but the radius is like root z, right? And so the radius changes as the height changes. Well, that's okay. It's perfectly good. It's root z cos theta and root z sine theta. And the z goes from 2 to 5. Perfectly fine. Yeah, it's kind of like a bowl, but with the bottom cut out. So here at 2, the radius is root 2. And then here at 5, the radius is root 5. It'll go something like that. I know it's curved because I will just say one other thing. I know it's curved because when I pick an x, when I pick y to be 0, I get z equals x squared. And so this is in fact a parabola shape, but only a piece of it. Because it only starts at 2. Yeah, if we started at 0, it would come all the way to the bottom. And if we started at -5, there wouldn't be anything down there. It would only start at 0 because you have to have a positive number there if you're going to have x squared plus y squared. Yeah, cool. So traditionally, they make it start at 0 because then it has a neat little hole. Because this one's got 2 edges, which is a problem. That means that if I did the Stokes' theorem on this one, I would have to do the 2 edges separately and include them in the calculation. Yep.
If there was x squared plus y squared equals z squared.
It would be straight. So just a second, z was from 2 to 5, and theta is from 0 to 2 pi. So if you've got x squared plus y squared equals z squared, that would in fact be a cone. Those edges would in fact be straight. Yeah. And that's because and it would be like z cos theta, z sine theta, z. And that's because at height z, the radius is z, and so this slope is always 1. Yeah. So that's pretty cool, actually. So from 0 to 9 or whatever. So once upon a time, you covered quadric surfaces in Maths 1B. And so once upon a time in Maths 1B, they had x squared plus y squared equals z squared, and they told you what that was. And I think that the people who are running MCC may have forgotten that that's not in Maths 1B anymore. Anyway, even though the curriculum changed in 2018, the curriculum for MCC didn't change in 2018. That was written in 2017, I think. Does it have Matt Finn on the cover as one of the authors? I think it does. He left the uni in like 2016. So, yeah. Yay. He works in weather prediction now. As applied mathematician. And multivariable calculus is a useful thing for that sort of thing. So these are the classics, the cone and the bowl, the parabolic bowl. There are lots of them, but ultimately, if you can look at it and see that x squared plus y squared, then that's a place to look for a circle. And say, well, at this height, and you could do it as z squared plus y squared equals x, and it will be the same, but it's going sideways. And so you can do all of those things. If you're given a parameterization and you're asked for the edge, like the boundary, then look at where the circles are, and it's usually one of the circles. I don't have an example off the top of my head, but there was one in the assignments. I hope that's helpful for making parameterizations. Oh, no, there's one more. Wait. What if you wanted to parameterize not a surface, but the entire of space? Or in particular, the inside of a sphere? The inside of the sphere, x squared plus y squared plus z squared equals 25. So that's a sphere. It's beautiful. What if you wanted to parameterize that? Now, you could, if you wanted to, locate an x, then locate a y, and then locate a z. That would get very frustrating because all of your answers for x, for y, and for z would involve square roots. And so there must be another way by thinking about this as being made of circles. So what you can do is you can imagine a circle at a specific height. going to be fine. So first I'll do the, instead of the inside, I'll do the surface of a sphere. So here we go. I'm going to imagine a specific height. And instead of imagining it at a specific height, I'm going to imagine it as an angle down from the top to make an angle down from the top because I know I'm going to come around this circle. So that's what I'm going to do. But also this circle is going to be cos theta sine theta times some radius. So from above, I've got the original sphere that I'm thinking about. And then I've got this circle at a specific height that I'm interested in. And so this is going to be, for some radius, it's going to be something times cos theta and something times sine theta, and it's going to be at some height. That's what the points on this circle are going to be. I don't know what goes in these spots yet, but I definitely know that that's the shape it's going to be. And what I need to know is what height it's at and what the radius is. And here's the magic trick that I love so much. From the side, it looks like this. And what I'm going to do is I'm going to call this angle phi. I think. Traditionally, it's phi. Oh, it is? How exciting. Yes, they do call it phi. Yay. Yay for all of us. Because theta is traditionally used for the one that's going around a full circle. So we're going to come phi down from the top. Yep. And what that means is that this radius here I know is 5 because it's a sphere of radius 5. And so this here must be 5 cos phi because the phi fits in here. And this must be 5 sine phi. But wait, that means that this distance is 5 sine phi because this line here from above is that line there. And so actually the radius is 5 sine phi and the height was 5 cos phi. Isn't that cool? So that is the surface of a sphere of radius 5. We're just still going on the previous seminar. So that phi goes from 0 to pi because we only have to come down here to figure out what the different, down here to figure out what the different radiuses are. And we don't have to worry about that side because that's covered by this rotation here. And the theta still goes from 0 to 2 pi. That gives the surface. But if you wanted the entire inside of the sphere, then you could imagine it as being a whole lot of spheres stacked inside each other of different radiuses. And so if you wanted you could have, they use rho, don't they? I'm going to use R, sorry. Because, you know, they use rho and then they use rho for density as well. And it's like, honestly, people. And so this is, the radius goes from 0 up to whatever the radius actually is. And the phi goes from 0 to pi. And the theta goes from 0 to 2 pi. And even though technically I used the phi and the r to tell me what the radius was of the little circle that I was at, overall I can choose the theta first And that just tells me what direction this slice is in, because I can slice it in all these different directions. So, yeah. This is a really good parameterization because these three directions are independent of each other. So yeah. And the cylindrical was exactly the one I did before, where r cos theta, r sine theta, but z is just z. So it's taken me a couple of years, but hopefully it's a little quicker for you, that I always, no matter what this diagram here looks like what the hell is that? Honestly. Like, how, that is not helpful. This maybe, I can see the theta going that way and the phi coming down from above, but this diagram is much easier for me to see what the phi and the theta are doing, because the theta's going that way. So theta from above goes round that way, phi from the side comes down this way. That's much easier for me to see what's going on. And they're trying to, with these vectors, tell you what direction the derivatives are going to go in, but I can do that as well. Theta, when I change theta, my point's going to go a little bit further around the circle, and so the r theta is tangent to that circle. So it stays flat, it's at that specific height. Whereas if I change phi, I'm coming down from above, and so r phi is tangent to the circle but coming down. And r is outwards because that's making the radius wider. Yeah. So it is useful to know what direction the three derivatives are pointing. All right, that'll do. And then I will take 10 minutes while everyone's coming in to deal with problem stat, to deal with that and talk about problem stats. Thank you. I will just stop that. Stop the recording.